My name is Andrew Blakers. I'm from the Australian National University. In this talk, I'm going to explain why I think that 100% renewable energy is much easier and cheaper than most people think. And the direct implication of this is that removal of 3/4 of global greenhouse gas emissions is much easier and cheaper than most people think. In 2020, solar PV and wind constituted 3/4 of global net generation capacity additions. All of the other generation capacity methods were relegated to the remaining 1/4. Solar and wind have comprehensively won the global energy race. Coal, oil, and gas cause about 3/4 of global greenhouse emissions. Solar PV and wind are by far the best prospect for rapidly driving coal, oil and gas out of the global economy. The silicon solar cell is about 95% of the global solar market and is going to be the largest single component of removal of greenhouse gas emissions from the global economy. All of the required generation and balancing technology is available off the shelf. Of course, there is lots of further work to be done to further reduce the cost. Fortunately, the cost is already so low and will fall further, and so the net cost of driving oil, gas and coal out of the global economy will be around zero. So let's have a look at how the various energy technologies are faring in the market. What you see here is a bunch of energy generation technologies, and the green, yellow, red, brown and blue curves are the net capacity additions in 2016, 17, 18, 19 and 20. So at the left-hand end you can see that solar photovoltaics and wind constituted 3/4 of global net new generation capacity in 2020. Gas is hanging in there at a much lower level than solar and wind. Coal is falling and falling as the economics of coal look worse and worse compared with solar and wind. Hydro has very poor long-term future as a generation technology because of limited numbers of rivers to dam and strong environmental pushback. However, hydro has a very important role for pumped hydro energy storage, which we will discuss later. Nuclear energy has come and it's gone. You can see that the amount of net new generation capacity from nuclear is in the range of a few gigawatts each year. Sometimes it actually goes negative because power stations close faster than they open. Really, nuclear simply cannot compete with solar and wind, not by a factor of 2 or 3, which is why the nuclear industry is now a cottage industry compared with solar and wind. Bio is a nasty form of energy generation except for waste because of its appallingly low efficiency and strong competition with food and ecosystems, and is bubbling along at a rate of a few 5 or 6 gigawatts of new generation capacity each year. Solar thermal failed in the global marketplace. It's barely visible on the graph. Geothermal has far too limited resource base to ever become significant except in 1 or 2 countries, and ocean is nowhere. So really the future of energy is solar and wind. They have such a large head start and they're growing so quickly that it is almost inconceivable that any generation technology can catch them in the next 20 or 30 years. Solar and wind are the technologies that will have to do the heavy lifting to get rid of oil, gas and coal from the global economy and save the world from really serious climate change. So about 3/4 of the world's population lives in the Sun Belt. This is the region from plus 35 degrees to minus 35 degrees of latitude and includes all of Africa, nearly all of Australia, nearly all of the populated area of South America, all of Central America, a small part of the United States, all of India, and about half of China, and all of Southeast Asia, and all of the Middle East. So that's 3/4 of the global population. The key point about the Sunshine Belt is that it lacks cold winter, and the ratio of solar intensity between summer and winter is small. So on the equator, there is no summer and winter. Towards the 35° plus and minus north and south, there is a winter, but it's not a severe winter, and you still get plenty of sunshine in the winter. So much has been written about the supposed difficulty of reaching high levels of solar in your electricity grid, and this is essentially written from the perspective of Europe or Northeast Asia or Northern America, which do not have very good sun in winter and also have very cold winters. Fossil fuel use causes about 3/4 of global greenhouse emissions, as shown in the pie chart. Solar and wind can displace all of these fossil fuels over the next 20 or 25 years. The first step is to decarbonize electricity. With this clean electricity, we can then electrify transport, heating, and industry. This means that sales of electricity have to double or triple. This is a substantial task, but it is a fairly straightforward task. It basically means lots of new solar, lots of new wind, lots of new transmission, and lots of new storage. All of it off-the-shelf technology. So let's have a look at zero emissions in 2040. A similar calculation applies to 2050. We'll have about 10 billion people on planet Earth in mid-century. And if we assume 100% electrification of everything, and that everybody enjoys a similar amount of energy consumption as developed countries do today, then we're going to be consuming about 20 megawatt hours per person per year, which adds up to about 200,000 terawatt hours per year for the whole of Earth. And I would expect that something like 2/3 of that will come from solar and 1/3 from wind. And that means we have to start installing solar at a rate of about 4 terawatts per year and wind at a rate of 1 terawatt per year. This is about 20 times faster than the current deployment rate. And we need to grow at about 30% per year to get to this point by the late 2020s. Well, in actual fact, solar and wind have been growing at this rate for many decades, and so it is entirely feasible that we can do the whole job, get rid of all oil, gas and coal, get rid of 3/4 of global emissions by simply doing and growing in a similar fashion to what we have been doing. It turns out that if the entire world was powered from solar photovoltaics, with a per capita energy consumption the same as in Australia or the United States or Singapore or some other developed country, and if all oil, gas and coal was driven out of the economy through electrification of transport and heating and industry, then about 60 square meters of solar panel per person would be required, covering about 0.1% of the world's land surface. Tens of billions of solar panels will be required to drive fossil fuels out of the global economy. Many of them will be on rooftops of houses and factories and commercial buildings. Others will be in arid areas such as southwestern United States. In densely populated countries, vast numbers can be used in combination with agriculture. The panels are located on tall poles in combination with pasture or crops and provide a few percent shading, which has a negligible effect on the production of many crops. And many panels will also be floated on calm reservoirs and in calm tropical seas. Wind turbines can be located onshore, of course, and increasingly offshore. Onshore turbines occupy almost no space, just a few tens of square meters per turbine. In the North Asia and Northern America and in Europe, there are vast possibilities for offshore and including floating offshore turbines that mean that countries like Japan can be fully self-sufficient for electricity production. This is a graph of the globally installed deployment of solar running from the year 2000 through to last year. So in the year 2000, there was 1 gigawatt of solar installed around the world. In 2020, there's about 760 gigawatts. We need to go from 760 gigawatts up to about 76 terawatts, which is another factor of 100 over the next 20 to 25 years. So we grew 1,000-fold in the past 20 years. We need to grow another 100-fold in the next 20 to 25 years. Solar PV and wind are variable electricity suppliers. Demand and supply must be balanced for every second of every year in order to have a stable electricity system. There are several ways of ensuring that this occurs when a solar and wind dominated electricity system eventuates. It's very desirable to have both solar and wind. The wind often blows at night, and of course when it's stormy weather, when the sun is not shining, the wind is blowing. Often when it's calm weather, it's fine and solar PV is generating. Together they are better than either alone. A second method is to have wide geographical dispersion, preferably over millions of square kilometers. For example, the European Union or China or the continental United States or North America. This hugely reduces storage by smoothing out local weather and demand. The third method is demand management, shifting loads from night to day and incorporating interruptible loads, for example, an aluminium smelter. Finally, mass storage. Pumped hydro is by far the largest method of storage for the electricity industry, 97% of all storage. Batteries are becoming important and there are many other viable options. The USA has great wind. The redder the better. You can see that there's a lot of wind on the coast and a lot of wind in the center. The USA also has great sun. Again, the redder the better. There's a lot of sun in the southwest of the United States. It's world-class solar resource. Transmission hugely reduces storage needs. Long-distance transmission beyond about 800 or 900 kilometers is generally via high-voltage DC cables. The state-of-the-art for high-voltage DC is a cable running at 1.1 megavolts over a distance of 3,000 kilometers, carrying 12 gigawatts of power with a 10% loss. The red line on the map of the United States shows that Texas wind power can be delivered directly to New York with such a cable or to the west coast. A network of high-voltage DC cables spanning the United States means that the amount of storage that's required to support 90 or 100% variable solar and wind will be reduced by a factor of 4 or 5. I'm going to spend some time talking about pumped hydro energy storage. The reason is that pumped hydro represents 99% of storage energy for the electricity industry and 95% of storage power. It's very likely that this will remain the case despite the rise of batteries, because pumped hydro is very cheap for overnight and longer storage compared with batteries. This is an example of an on-river pumped hydro system. We have an upper and lower reservoirs separated by 151 meters. This is called the head, 151 meter head. So water can flow down through those pipes to generate electricity, and at other times when it's windy and sunny, the pump turbines can reverse themselves and pump water back up to the upper reservoir. So water can cycle backwards and forwards indefinitely between the two reservoirs with a round-trip efficiency of about 80%. This means that about 20% of the stored energy is lost in a round-trip cycle. Off-river pumped hydro is an alternative, no river in sight. So this is a good example from Italy. The head, the height difference between upper and lower reservoirs is now 500 meters. Similar water volume to the previous with 6 gigalitres, combined reservoir area of only 1 square kilometres, which is 19 times smaller, and it's got a gigawatt rating, power rating, and can run for 6 hours flat out. So comparing off-river and on-river pumped hydro energy storage, there are vastly more off-river sites, 100 times as many, because 99% of the Earth's surface is not on a river. There are low or zero flood control costs because you're not on a river. Pumped hydro that is off-river is basically for daily storage. So a 100-hectare pair of reservoirs, 25 meters deep with a 500-meter head, can operate at 2 gigawatts for 12 hours. If you want seasonal storage, then an on-river system is probably a better way to go. Importantly, for off-river pumped hydro, the heads are typically better. You can double the head by putting the upper reservoir not in a river valley, but on the hills around the river. And if you double the head, then you double the power and you double the energy storage, but you don't double the cost. So large head is important for reducing the overall cost of storage. ANU's Global Off-River Pumped Hydro Atlas lists 616,000 sites all around the world, comprising 23 million gigawatt hours of storage. This is 1 million gigawatts for 23 hours, an enormous amount of storage, all outside national parks and urban areas. Roughly speaking, this is 100 times more storage than the world would need to support a 100% renewable energy system. The United States of America has 35,000 sites with combined storage of about 1.4 million gigawatt hours. This is about 200 times more storage than the United States needs to support a 100% renewable energy system. If you open the Global Atlas, you can zoom and pan to find the details of individual sites. So in this slide, we are zooming into Western United States and zooming further into the Denver region. As you zoom in, the individual pairs of reservoirs resolve themselves. And if you zoom in far enough, you can see each individual reservoir, you can see the dam wall, you can see the tunnel route, and clicking on the tunnel route or clicking on the reservoirs produces pop-ups that contain a wealth of information about each site. So all of this information for 616,000 sites around the world is available for visualization and for download. In our atlas, all of the sites are outside national parks. It's important to understand that the land and water requirements of pumped hydro to support variable solar and wind are small. So we've looked at this for Australia, and in Australia, you would need about 3 to 10 square meters per person of reservoir area to support a 100% renewable electricity system, based mostly on variable solar and wind. This is much smaller than the area of land required for the solar and wind farms that the pumped hydro supports. The water requirement is small. It's about 3 to 10 litres per person per day. And this is primarily for the initial fill of the reservoirs and also to make up the loss of water to evaporation in Australia's hot, dry climate. These are really small quantities of water in the overall scheme of things, and they're much smaller than the amount of water required for a coal-based electricity system because there are no cooling towers. I've now introduced the key technologies of the solar and wind revolution. These are solar PV, wind, pumped hydro energy storage, batteries, and transmission. The benefit of this quintet of technologies is that they are mature, they come from vast production runs, there's effectively infinite material supply for each of them, there's effectively an infinite resource base, and they have low environmental cost. There is nothing to invent. They produce the cheapest energy in history already, and there's lots of room to further lower costs. Importantly, no arm waving is required to point to these technologies as the solution to 3/4 of global greenhouse gas emissions. Let's have a look at where things are happening faster than in other places. So this graph shows the renewable deployment speed in terms of new watts per person per year in 2020 for a whole bunch of countries. So the red is the photovoltaics, wind is green, and hydro is blue. And the larger the bar, the faster is the amount of renewable energy deployment in 2020. So Netherlands, Australia, and Norway were well ahead of the rest of the pack, putting in solar and wind at about 3 to 5 times the rate of China or the USA or the European Union or Japan, and 10 times the global average rate. There's no reason why this can't continue and indeed double, and that is actually going to be required for reaching zero emissions from energy production, in other words, zero oil, gas, coal, by about 2040 or 2045. So we need to get up to about 600, 700 watts per person per year of deployment rate to do the whole job before mid-century. And this is not so hard, considering that several of the leading jurisdictions have trebled or quadrupled their deployment rate of solar and wind over the last 5 years. We've just got to do it again, and then we will be on track for very deep emissions reductions by mid-century. So Australia is a particularly interesting country to look at to see how balancing of high levels of solar and wind is proceeding. The reason for this is that it is physically isolated from any other country. It can't trade solar and wind for imported fossil or nuclear electricity. It has to go it alone. So Australia has reasonably good solar and wind resources where people actually live. This is on the eastern and southern coastlines, mostly within 200 or 300 kilometres of the sea. The blue line is a cartoon showing where about 80% of Australia's population lives. So typical capacity factors for well-sited wind farms in this region of Australia is 40%, maybe 50%, and the DC capacity factor for single-axis tracking solar is in the vicinity of 20 to 24%. So it's reasonably good by world standards, but very far from being uniquely good. The flood of renewable electricity into the Australian national electricity market is having a dramatic effect. So in 2021, renewables reached 30% of all generation on a 6-month moving average basis, and this is headed for 50% by 2025. The price of electricity on the wholesale spot market is around $35 per megawatt hour US, both for current price and also for the futures market price in 2024. Gas generation is falling and is around about 5% at present. It is not true that gas is required to support a solar and wind dominated system. In South Australia, The renewables fraction reached 70% over the summer on a 6-month moving average basis and is headed for 100% in 2025. Again, the price of electricity is around US $35 per megawatt hour on both a current and 2024 futures price basis. Again, fossil gas is falling and falling as solar and wind rise and rise. There is no hydro or nuclear or coal in South Australia, or bio for that matter. So it truly is a remarkable world-leading jurisdiction of about 1.7 million people with a weak connection to the rest of the national electricity market. Australia has abundant off-river pumped hydro opportunities, about 4,000 good sites, 180 terawatt hours of total storage capacity, which is about 300 times more than needed to support 100% renewable electricity. So Australia really has a wealth of opportunity for deployment of pumped hydro storage. In response to the rise and rise of solar and wind in Australia, new Australian LNG infrastructure is being developed, and pumped hydro is leading the pack with 3 existing pumped hydro systems, 2 new systems under construction, and about a dozen systems under detailed planning and feasibility studies. The Snowy 2.0 system, for example, under construction at present, is bigger than all the utility batteries in the world put together on an energy basis. None of these pumped hydro systems entail new dams on rivers. Utility batteries are starting to make significant inroads, destroying the market for gas load following. And new transmission is becoming ever more important to connect states to states, to smooth out local demand and weather, and also to bring new solar and wind from renewable energy zones into the cities. Many models have looked at the cost of balancing high penetration of solar and wind. Unfortunately, virtually all models fail to include the mature, abundant, low-cost, low environmental impact off-river pumped hydro energy storage technology. The consequences of this are that the cost of overnight storage is inflated, the amount of destructive bioenergy required is also inflated, and immature technologies are included that require a lot of arm waving about future scale and future costs. This is not to say that pumped hydro will necessarily be overwhelmingly dominant in future storage markets. It simply means that if you're modelling a high solar and wind penetration grid now, you should model it on the basis of off-river pumped hydro, because it is a now mature, viable, low-cost storage option. In the future, if something turns out to be cheaper than off-river pumped hydro, then that's good. It simply means that the model will have over rather than underestimated the cost of balancing, and the cost of energy will be lower than modelled. We've looked in detail at the cost of balancing 100% renewable electricity in Australia. The modelling would be generally applicable to any other large area country with plenty of solar and wind, such as the United States. The balancing costs in our modelling comprised pumped hydro energy storage, high voltage DC transmission, and occasional spillage of solar and wind. If other forms of storage become available that are cheaper than pumped hydro storage, then the cost of the modelling presented here will be an overestimate. We found that until you get up to about 3/4 penetration by variable solar and wind, then the cost of balancing is low, only about $5 per megawatt hour. As you go from 3/4 up to 100% solar and wind, the cost rises to about $20 per megawatt hour, because a lot more storage and high voltage transmission is required to service the remaining 1/4 of solar and wind. Generation from solar and wind in good sites now is around about $30 per megawatt hour. This has to be added to the $20 per megawatt hour for balancing 100% renewables, giving a total cost of energy of $50 per megawatt hour, which is competitive in most places of the world. Now I come to the summary of my talk. Solar and wind are now 3/4 of global new generation capacity, and this is likely to increase into the range of 90% over the next few years. Electrification of everything using solar and wind allows the elimination of fossil fuels from the global economy and the removal of 3/4 of global emissions. Putting a lot of new solar and wind into an electricity system of course causes declining emissions, but also declining prices, because solar and wind are so cheap compared with existing fossil fuel and nuclear fuel electricity generators. Balancing high levels of solar and wind is straightforward using off-the-shelf techniques. This includes hydro and pumped hydro, the latter being mostly off-river, batteries, transmission and demand management, and a whole range of other things at a minor level as well. Getting to 100% renewable energy system is going to be much easier and cheaper than most people believe. What is happening in Australia is instructive. Here is a country with a government that is not keen on renewable energy. However, solar and wind are running right over the top of federal government policy and preferences because of the compelling economics of solar and wind. The fastest energy change in history is underway. Thank you.
Okay. So just a quick note, please do, any of the attendees, any of the participants, panelists, please do put any comments or questions in the chat box and I will address them during the session. I see there's one already, but I'm going to jump in quickly. We have Professor Matthew Stocks, who is one of Andrew Blaker's colleagues, joining us today to take the live Q&A. So Dr. Stocks, I enjoyed the presentation and all the interesting work. I did want to, on the one hand say, note the importance of adequate representation of land trade-offs. So appreciated the fact that it was, that you noted the fact that there's a lot of things that people presume are not usable in terms of land and solar and wind, but are vastly, can lead to overestimations. Such as photovoltaics and the fact that wind farms can actually have co-use. At any rate, major challenge with any energy source is the question of siting. I did note that, after this discussion, it must be challenging with these large-scale databases to incorporate individual siting decisions, because we know that for pumped hydro, while we can identify the exact locations and it can be abundant in specific locations, the conversion of areas to these additional dams might be challenging. So I'm wondering, in terms of the databases that were developed, the global databases in particular, where it would be more challenging to determine whether there are siting decisions, if you have any plans to start to incorporate potential challenges in this regard.
So the challenge there is very much the local issues. So every individual country will have its own philosophy in terms of what is acceptable and what isn't acceptable in terms of building such sites. So at this point, no, we haven't looked at trying to roll that out at a global level. What we've tended to do is work with local jurisdictions around how they see that needs to be handled in terms of their own philosophy and their own beliefs in terms of what's important in terms of deploying this sort of technology. One of the important things to recognise here is that what is in the Atlas is also probably about 2 or 3 orders of magnitude more than is required to balance variable renewables, and therefore if you find a particular site has a cultural concern or a social concern or an environmental concern, then there's probably another site 5 miles down the road which you can examine and see whether that's going to be a better suit to the needs of that region.
And I could keep asking you questions for a while, but there already is one in the chat, and please do, for those participants, add anything in the chat. We do have one question. Really great point, actually, because always there are questions of people, seeing futures for specific technologies. So This question comes from, it might be a student, I'm not sure, but says, many thanks for your presentation, Professor. Previously, Prof. Jacob Poe, I hope I pronounced it correctly, I've read his literature, has implied that without nuclear energy, the climate goal can hardly be reached. So questioning, why is there this apparent contradiction, and nuclear is so important, but 100% renewables is so easy. Can you comment on that? And additionally, do you think a global energy network is necessary for practical and efficient performance of renewables, especially for solar and wind? So if you could comment on those two questions, that would be great.
So I think if you were asking me exactly the same question 20 years ago, I would have said nuclear is going to be a key part of the solution. The price of wind and solar were comfortably higher than the cost of fossil fuels and nuclear, and the solution was very much being pushed towards nuclear being necessary. I think what we're seeing, though, is a very different solution emerging as we see the cost of wind and solar just continuing to drop and being directly competitive in the markets. So the challenge we see, sorry, personally I see with nuclear is cost. And that if you look at what the cost of deploying wind and solar with storage so that you're delivering energy continuously, it's now lower than nuclear. And the other challenge there is that nuclear doesn't play well with solar. The two technologies don't complement each other well, because solar fundamentally is a variable technology that's going to produce its energy in a very limited window, whereas nuclear really needs to operate 24/7 to act reliably. It doesn't like strong ramps to turn on and off with the strong ramps associated with solar. So our own work suggests that it's not needed. That there may be different jurisdictions where they take the view that that's not possible. You could imagine in Japan, the land use challenges with solar, you might see that nuclear ends up playing a bigger role there. But we've seen the challenges that Japan is having around incorporating nuclear in their future planning.
Yeah, and go ahead.
So in terms of coming to the global energy network question, solar really doesn't need a global energy network. So the modelling we did for places like the US and Australia, where there's a strong wind component, you can see the benefits of transmission, that weather systems tend to move on the scales of thousands of kilometres, and so the wind will be blowing in one location and thousands of kilometres away, the wind won't be blowing. And so being able to move energy long distances is important. When we've looked at tropical locations, which is where the bulk of the world's population is, what you see there is that the variability of solar is very low. So both on a seasonal basis and on a day-to-day basis. And what you find there is actually very little benefit in transmission. We modelled through Southeast Asia, for example, and what you find is that the cost of the transmission is almost exactly the same as the cost of storage. You're just trading off one for one in terms of developing long-term reliable systems based on hourly level modelling. So the more solar you have, the less you need transmission to meet your needs. And the tropical areas are just dominated by solar because of the low wind resource in those areas. So less need for global systems there. It's more beneficial when you start to look at systems which are more in the temperate zones where wind is playing a bigger role. So Europe, the US, Northern China, and to some extent Australia.
So I'm going to suggest that Dr. Venkhaus, if you set up share your screen for your presentation as I'm asking the last question, that would be wonderful. Quick note, we are so fortunate in this day and age to actually just be able to say how competitive renewables are. So every single time that we can say that, I think it's just so amazing in comparison to 10, 15 years ago. I'm going to take one last question because we want to, for the interest of time, but do add them because we might come back to them. Where has it gone? Oh, I wonder, so always a big question when you're modeling the future of renewables. So someone says, hey, that's great. You took a look at the amount of energy that would be needed, but are you taking into account capacity factor of particular given sources, which is always a question when we start to think about the capacity required for solar and wind.
Yeah, so the sort of modelling work that we do looks at very long-term energy history and uses that as a basis for working out what the energy generation might be in the future. So we're looking at 20 to 40 years of historic weather data to determine what how the wind and solar might behave over long periods of time. So we consider the real capacity factors of those technologies and then determine the amount of transmission and the amount of storage that's required to balance those and meet the either the electricity or the entire energy demand associated with the electricity needed.
Okay,
I do have one quick question.
Sure.
Sorry.
Yeah.
Yeah. So, is the fresh water required for the pumped hydro, and no salt water?
So there's lots
what
of
I'm really driving at is like if you attribute the total area of the exposed freshwater area, how much is compared to the lake area, let's say over the world, and what kind of evaporation rate? Because I understand you also have this evaporation suppressors.
Yeah. So one of the things we don't really fully understand is just how much water we use for our existing thermal generators. So coal and gas use a lot of water for their steam processes and a lot of water for cooling. So if you actually go through and look at how much water would be needed in an energy system to replace all of that evaporation and water associated with pumped hydro, it would be about a factor of 10 less than we already use in the power system today. So it's not so much about we need this new abundant source of water. What we need to do is just reallocate a fraction of the water that we're using for existing thermal generation and to use it for energy storage. So it's actually a lower water use than we're using in the system today. It's a few square meters of reservoir per person. It's not a huge amount of additional water required for pumped hydro.
Thank you.
Okay, and thank you, Dr. Stocks. If it would be fantastic if you, I know it's a time difference, but if you could wait, because there were more questions from you, do feel free to respond in the chat as well, if you so wish, but there may be additional questions to you at the end. I'm going to pass, thank you so much.